Hello and welcome. In this video session, we will begin a new topic on thread synchronization. We will understand what is a thread synchronization and why it is required, and what are the different methods that can be used to achieve thread synchronization. So some of the methods of thread synchronization we will be studying are mutex or mutual exclusion and condition variables, which work on wait and signal method. Now let's see the synchronization in threads. So as we have seen the basics of thread, that multiple threads can execute in a process, and the threads share the global variables. That means the thread has access to the data segment, the heaps and the heap segment. So the data that are defined in this memory segment can be accessed across the threads. So in this case, whenever the thread tries to access these resources, we have to take care of the synchronization between the threads. Otherwise, inappropriate results can occur. So we have seen in the previous video sessions that in order to achieve synchronization, we have to write the code in a critical section manner, and we have to maintain the atomicity. So we can say that a piece of code is in a critical section when its execution is not interrupted by other thread execution. Now let's see some of the incorrect method of multi-threaded programming where synchronization issues can occur. Let's see this with an example. Now let's see the incorrect method of using global variables, and which can cause potential synchronization issues. So in this program, we include the required header files, and we have a global variable GLOB. This can also be considered as a shared resource because this variable can be shared across the different threads. Here, let's begin with the main thread here. So the main function can be considered as a main thread, and we declare T1 and T2 of type pthread underscore T, and we create two threads here, pthread create passing T1, and similarly create pthread create passing T2, and we specify thread func1 for T1 and thread func2 for T2, and then later the main thread waits for T1 and T2 complete by calling pthread join, and then finally the main thread exits. Now let's go to the thread definition. We have thread func1 and thread func2. In this, each thread it executes for a loop for 0 to 10,000 as specified here. So what happens in the loop is it takes the global variable to the local variable here, and whatever is the global value, it is copied to the local variable, and it increments the local variable and puts back the value to the global variable. Similar thing is also done in thread func2. The loop runs for 0 to 10,000, and it takes the value from global and stores to the local variable and increments the local variable and puts back the local variable to global, and then once the loop is finished, it returns. So now what we can expect is what as a user, as a programmer, we expect is, so let's say the global count is 0. So when it runs for 10,000 times, this thread and this thread runs for 10,000 times. So at the end of the execution, we will be expecting that the global value will be 20,000. So let's compile this and see the output. Let's create the output file here. As mentioned, we should link with pthread library. Now we have the output file. Let's execute this. Okay, first execution we got 20,000. Second execution we got 13,999. Again we got 20,000, 15,846. So in different executions we are getting different values. So this means the output what we are getting is not we are not getting the same output in every run. This means there is a synchronization issue here. If we note here, every time the global variable value is different. Sometimes it gives the correct value, sometimes it gives the different value. This means that the code here is not running in a atomic manner. So we have to, whenever we access the global variable, we have to, for example, in this code, we can say that these 3 lines are the critical section, and this should be accessed in an atomic manner. This means when the thread enters execution this line, this should not be interrupted by any other thread. For example, let's say that what is happening is, let's say that first thread has copied the value to location here. When it is about to execute this line, if this thread is scheduled, then the global value will be copied here is the old global value. It will not be the one which is same as here. So then it increments, then it puts back the global value here. So now the global value has different value than what is stored in the local value here. Hence, there is a synchronization issue in this program. Now, let's go back to our presentation. So here we see that this is an example in which it is an incorrect way of multi-threaded programming, which can cause the synchronization issue while accessing the global resource. This is what we have seen. So now, let's see what are the different methods of writing the code in a synchronization fashion. So one of the method used to synchronize between the threads is mutex. So mutex is nothing but it's a type of a lock, and its data type is pthread mutex _ t. So mutex helps in running the critical section in an atomic manner. The mutex has basically 2 states, that is a locked state and an unlocked state. Now, one more important thing about the mutex is only the thread which has locked becomes the owner, and the owner thread only can unlock the mutex. So now let's see the operations of the mutex. So the thread that needs to access the critical section, it first needs to lock the mutex and then access the shared resource and then unlock the mutex. So this 3 steps will help to gain the synchronization between multi-threaded programming that needs to access the common resource or the shared resource. Now let's see how this works here. So now let's consider we have 2 threads, thread A and thread B, running in a multi-threaded fashion. Now we are not sure which thread will be which thread runs at what time, or we can say that we are not sure when the thread will be scheduled. Now let's say that if thread A is scheduled first, and now it locks using the mutex m, and now after locking, if the lock is successful, it now proceeds to access the global variable. Now let's say when the thread A is accessing the global resource, now if thread B is scheduled, now similarly it tries to lock the mutex m, the same mutex what is used here. When it tries to lock the mutex, since the mutex is already locked, this cannot lock the mutex once again. So thread B blocks on the mutex m and the lock is not granted, and it keeps on waiting in a block state or in a sleep state until it gets access to the mutex. Now here the thread A finishes the accessing or the modification of the global resource and then unlocks the mutex. And once the mutex is unlocked, now the thread B, which had tried to lock the mutex, will now get unblocked, and now the lock is granted for thread B. And the lock owner is now thread B. Whoever gets the lock or gets the grant to lock will be the owner of that mutex. Now in this case, thread B is the owner, and further it tries to access the resource, and after accessing or modifying the resource, now it unlocks. So now we can make sure that this global variable is protected by the locks, and now this section of code from here to here runs in an atomic manner, and this is a critical section. So the section of the code in which the common resources are accessed can be considered as the critical section, and in order to achieve the atomicity, in this case we can use the logs so that synchronization can be achieved. Now let's see the program concepts of mutex. So in this case we will discuss the statically allocated mutex. So we have two types of mutex, basically static allocated and dynamic mutex. So here we will be considering only the static mutex. pthread mutex underscore t is the data type of the mutex, and let's call the variable name as mtx. So we need to initialize the mutex pthread underscore mutex underscore initialize. So this initializer will tell that mtx is a type mutex that is statically allocated. Now let's see the syntax of the mutex. So in order to use the mutex, we need to include the header file pthread.h, and as we have seen in this example that we, after declaring a mutex, we are performing lock operation and a unlock operation on the mutex. So we have pthread mutex lock and pthread mutex unlock on the mutex variable. So this is a mutex variable, and we need to lock on this mutex variable and unlock the mutex variable. So both this function call returns a 0 on success. If there is an error, it has a positive number. It returns a positive number on error. Also, let's see what is a deadlock. Now, consider two threads running, thread A and thread B. Now, let's say that thread A needs two mutex locks, that is lock A and lock B, in order to access the shared resource. Similarly, thread B also needs lock A and lock B in order to access the shared resource. So here in this case, thread A locks the mutex variable mutex lock A, and then it is about to put a mutex lock on B, mutex lock B. Meanwhile, if thread B has already put a lock on mutex lock B, now thread A waits until the mutex lock B is released. Now this thread A is waiting for thread B to release its mutex lock B, whereas in the same way thread B now goes further and tries to lock mutex lock A, but mutex lock A is already locked by thread A. So thread A has got mutex lock A and thread B has got mutex lock B. When we say got mutex lock, that means the thread A has put a lock on mutex lock A and thread B has put a lock on mutex lock B. Now when thread A is executing this, it will block because this lock is already locked by the other thread, and this lock, that is the mutex lock A, is already locked by thread A. So both the threads are waiting for each other to complete. Now this is called as a deadlock, where it keeps on waiting indefinitely for the thread that is acquired by the other thread to be released. Now let's see what are the methods or what we need to follow in order to avoid the deadlock. So in order to avoid the deadlock, we need to define the mutex in a hierarchical fashion. This means we need to try to have a same sequence of locking on the mutex. So for example, let's say that in the previous deadlock situation, we saw thread A is putting a lock on A, then on B, thread B is putting a lock on B, then on A. Instead of this, if we follow the other manner, for example, thread A puts a lock on A, then on B. In the same way, thread B puts a lock on A, then puts a lock on B. Now this is a locking in a hierarchical manner. So now let's say thread A has gained to put a lock on mutex lock A. Now if thread B also tries to put a lock here, thread B blocks because mutex lock A is already locked by other thread. Now thread A can proceed further and put a lock on mutex lock B. As a result, thread A can access both mutex lock A and mutex lock B and perform the operation on shared resource and then unlock mutex lock B and mutex lock A. Then the thread B which was blocked for mutex lock A can acquire the lock, both mutex lock A and B, and perform the operation on shared resource and then unlock both the locks. So by this, by following an hierarchical fashion of locking the mutex, the deadlocks can be avoided. Now this is the function call similar to mutex lock, but it has a slightly small different variations than the pthread mutex lock. So we have pthread mutex try lock and pthread mutex time lock. So the pthread mutex try lock is one in which it tries to put a lock, and at that moment, if the lock is being locked, if the mutex is being locked by some other thread, it does not blocks the function. Instead, it returns. It returns with a error saying that it returns with code EBC. Similarly, the function pthread mutex time lock, this is also similar to pthread mutex lock, but in this case we can specify the time in which it can get blocked. So when a thread calls pthread mutex time lock with some time parameter here, it tries to put a lock on the specified mutex variable. If that mutex is already been locked by some other thread, it waits for the duration that is specified in this function call, and even after that duration, if that lock is not available, then it returns to the calling thread with the error code e-timeout. Now let's see some of the examples of pthread mutex lock. In this program, we will see the pthread mutex, and this can be used for synchronization. This program is similar to the previous program, but in this case, we have taken care of achieving the synchronization. So here we have a global variable. Also, we are defining a new mutex variable. MTX is the mutex variable of type pthread mutex underscore t, and we have initialized with mutex initializer. So this is a static mutex. Now let's go to the main thread here. The main thread begins with defining two threads, T1 and T2 of type pthread underscore t, and it creates both the thread and calls the function threadfunc1 and threadfunc2, which is defined here, threadfunc1 and threadfunc2, and then further the main thread calls a join to both T1 and T2 thread. Thus the main thread waits until both the thread that is created has exited. Now let's go to the definition of both the threads. If you see the difference between the previous program and this program, we can see that before performing the operation on the global variable, we are putting a mutex lock, and then we are performing the access to the global variable, and then we are unlocking the mutex. So MTX is the global mutex that is used. Similarly, in thread function 2 also, this is the critical section. That means this is the piece of the code that accesses the global variable GLOB, and before accessing that, we are putting a lock, same lock that is the global, that is the variable MTX, and then unlocking by the same mutex variable. So now what happens is, as soon as whichever thread accesses the lock first, let's say that function 1 has got the lock. So once this lock is put here, now if the other thread tries to put a lock here, now this thread is blocked. That means it cannot further execute the other codes, other part of the code, and it waits in this line only until the lock is being released by the other thread here. Now let's run this program to understand the behavior. Now let's compile the program. Now let's run the program. We can see that the global value is 20,000. So any number of time we execute, the global variable value will be 20,000. So we are seeing that the global value is always 20,000. But in the previous program, we saw that the global value is not 20,000. This was 1_MUT was the incorrect way of multi-threaded programming, where there was a synchronization issues. So by using mutex lock, we are having a proper way of synchronization between the threads. So in this case, anytime we run, we are getting 20,000 only. Now let's see one more example. This program is similar to the previous program, but one thing what is different here is, here same in a similar manner we are creating two threads, T1 and T2, but if you note here, both the definition of the thread are same here. So the text segment of both the threads are same. We are not using two separate functions for thread 1 and thread 2. Instead, we are having a same function that is shared between thread 1 and thread 2. So this behavior is also similar to the previous code. So this is more efficient way of writing the code, where we are trying to put all the common code of thread function in one function. Let's compile this as well and see the output. Now let's run this. We can see that the output of the global variable is always 20,000. That means each thread has incremented the global variable by 10,000. And now we have one main thread and two threads running. That is T1 and T2 both share the same text segment code. Hello and welcome. In this video session, we will discuss on the condition variables. Condition variables are Hello and welcome. In this video session, we will discuss on the condition variables. Condition variables are a type of signaling and waiting mechanism. A condition variable allows signaling from one thread to the other thread, and the other thread keeps waiting for the signal to arrive, and once the signal arrives, the other thread takes the appropriate action. So in the previous video, we saw the mutex lock. Also, the sequence of execution of threads is not in user's control, because the threads can be scheduled in any manner. But when we have some use case where a proper order of execution of threads has to be followed. For example, let's see example of a producer and a consumer where first producer thread needs to be executed and the output of the producer thread needs to be consumed by the consumer thread. So in this case, the producer thread needs to be executed first and then the consumer thread needs to be executed after the execution of the producer thread. In this case, we can make use of a condition variable where the producer thread makes use of the signaling mechanism. Once the data or the buffer is being produced, it signals the change and the consumer thread waits until the signal is being received. Once the signal is received, the consumer thread uses the buffer of the producer thread. Also, a condition variable is always used in conjunction with the mutex. So whenever the consumer thread is waiting on the signal, it sleeps or blocks until the signal is received. So let's see the statically allocated condition variable. So condition variable, the data type of the condition variable is pthread underscore cond underscore t, and we have to specify the value of pthread underscore cond underscore initializer. So this is the static condition variable. So we have two types of condition variables, that is statically allocated and dynamically. So we will be discussing on static condition variables. So the main principle behind condition variable is signal and wait. The signal operation is performed by the producer and it is kind of a notification to one or more of the threads saying that the shared variable's state has been changed and now the other thread can access the shared resource. The wait operation is a method of blocking until the signal is being received from the other thread. Let's see the syntax of condition variable. So we have two types of operations. One is the signaling operation and the other is the wait operation. This function pthread condition signal is used to signal to the other thread, and pthread condition wait is the function which is being used by the thread that needs to be blocked until the change of the global variable occurs. So we need to include the pthread.h, and the syntax is pthread condition signal and it takes the condition variable, and pthread condition wait, and the pthread condition wait takes the condition variable along with the mutex. Let's discuss why we have to use the condition variable along with the mutex. So on success it returns a 0 or a positive number if there is an error. Now let's see the working of the condition wait, pthread condition wait function call. So in this case we have a condition variable cond and a mutex. So whenever a condition variable is called by the thread, this is usually called by the thread which is waiting for the change of signal that is occurred by the other thread. In this case, the first step would be the thread calling this pthread condition wait unlocks the mutex m. So whenever the mutex is locked, first thing will be the unlocking of the mutex. Then the second thing will be blocking of the condition variable on cond until it receives a signal from the other thread. So step number 1 and step number 2 is performed in an atomic way. This means when this pthread condition wait is performed, the step 1 and 2 is performed in such a way that no other threads can interrupt the execution of the pthread condition wait. Once the function waits blocks for the condition variable, now it waits for the signal, and as soon as it receives the required signal, it again locks the mutex m specified in this. So we can see the example in order to understand the working of condition variable. So in this case, let's open the program. So here we are including the required header files, and as we can see, we have two types of variable. First is the mutex and the second is the condition variable. So the mutex we have already discussed in the previous video session, and this is the variable of type pthread underscore cond underscore t. That means this is a condition variable, and both are used in a static way. So for mutex we need to specify pthread mutex initializer, and for the condition variable we need to specify pthread cond initializer. So both are a static initializer. Now we have a flag to signal the change of the state, and let's say we have a global buffer variable, and here let's begin with the main thread. The main thread in this case creates a pthread A and pthread B, and the thread A and thread B starts execution from its function, that is thread A and thread B, and the main thread waits for both the threads to complete the execution. Now let's go to the definition of thread A. In this case, thread A is the producer thread and thread B is the consumer thread. In this case, thread B has to execute its critical section only after the producer thread has produced the data. So here our use case is in such a way that even though we don't have the control on the scheduling of the thread, we have to make sure that the sequence of execution is as per the requirement. So in this case, first the producer thread has to produce some data in the buffer, then after producing the data, then only the consumer thread has to read the buffer data. So now let's see how to achieve this. As mentioned, we need both the mutex variable and the condition variable. In this case, let's say that the producer thread, that is thread A, is executing, and the producer thread puts a lock on my mutex variable, and then as soon as it puts a lock, it tries to fill the buffer with some required data. And meanwhile, before this, the value of done flag will be 0 in this case. So before executing of any of the thread, the flag value will be 0. Now let's come to the consumer thread. In consumer thread, we have to put a lock, then we have to check on the condition variable, and this is the flag we have to check on, and we have to wait for the condition variable by specifying condition variable and the mutex. So we have to specify both the condition variable as well as the mutex. So now let's go back to the working of this function pthread condition wait. So now what we had discussed is the first step would be it unlocks the mutex specified here. So when this function is called, it first unlocks this mutex. So in order to unlock this, we have to call a lock of this mutex before it unlocks. So the locked mutex here will be unlocked here, and it waits for this condition variable. So this unlocking and locking is done in an atomic manner. Now the lock is being unlocked, and the producer thread can now get the lock and produce the required data. And now once the required data has been produced, it can change the state of the variable to 1, saying that it has now produced the required data, and then it sends a signal on my con var, which is nothing but a condition variable, and then it unlocks. So once the producer sends a signal here, it unblocks this statement, because by this statement it is waiting for a signal on this variable, and this signal is being sent from the producer thread now. And once the signal is received here, now the next step would be to lock the mutex. So now as soon as the signal is received, it locks this mutex. Now the mutex owner is thread B, and then the thread B consumes the shared buffer, and then finally after consuming the buffer it unlocks. Let's compile this once and see the result. Now let's run the program. Now we can see that in this we are printing the critical section regions where it is required. So this is the critical section. In the critical section we are locking and then unlocking. So this part is the critical section, and in this case this part is the critical section here. So if you see here, the scheduling of the thread is not in our control. It can schedule in any manner, but critical section execution of thread A occurs first, then the signal is received from thread A, and this statement is always executed after the thread A executes. So we can see that in thread B we are reading the buffer that is produced by thread A. Now even if we run for any number of times, we will get that thread A's critical section is first executed, then only the thread B critical section is executed. So any number of times we run, we can see that thread A's critical section will be executed first. If we observe in this, thread B is scheduled first before thread A schedules. Even though thread B is scheduled, we are making sure that the critical section first executes thread A, then only the thread B critical section executes. So here we are maintaining the sequencing of critical section execution. If we go back, let's go back to the program here. Now let's try to analyze this in other way. Now let's say that, let's consider the case where thread A has scheduled first. So when thread A has scheduled first, now thread A has got the lock, and when thread A has got the lock, it now puts the data to the buffer. So meanwhile, the done flag is still equal to 0 here. Before this statement, the done flag equal to 0. Now let's assume that thread B has scheduled and it has put a lock, but when it is trying to put a lock, the lock owner is already thread A. So thread B blocks here, and now the done flag is 1, and now the condition variable is set and it unlocks. As soon as it unlocks, the thread B gets the lock, and then it unlocks this, and since the signal is already received, it locks again and consumes the global variable. Now let's assume that first the scheduling is in thread B. So now let's say that the thread B has put a lock initially on my mutex, and now done flag is equal to 0. Now this done flag is equal to 0, so it executes this line. So here, by executing this line, the owner of lock was thread B. Now it unlocks this thread, unlocks this lock, and now waits for the signal on this condition variable. Now as soon as the lock is being unlocked by thread B, the thread A, when it is scheduled, can get the lock, and now the owner of the lock is thread A, and now the thread A produces the data and it signals on condition variable and then unlocks the data. As soon as it unlocks and sends the signal, the thread B, which is waiting for the signal, receives the signal, and now it locks the mutex, and then it performs the consuming of the buffer, and then it further unlocks the mutex. By this, we can make sure that the producer and consumer thread is following a sequence of execution.